Where were you, Katie? All right, there we go. We're recording this time. Okay. So anyways, so good. So the capacitance of a capacitor then basically has to do with how much this thing can actually take. So basically the capacitance has to do with the charge, and it turns out that the capacitance has nothing to do with charge or potential. The capacitance is actually only dependent on geometry. So the slope of this line here, M, is what we call the capacitance of a capacitor, and it turns out this only depends on geometry. Depends on geometry. So meaning it doesn't matter how much potential I put or how much charge I put on there, because those two things are related to each other. It only depends on the geometry. And that's actually what you're testing in the first part of this in the first part of this lab here, but we'll talk about this a little bit more. So what are applications of capacitance? Capacitance or capacitors are used in circuits all the time. So let's talk about uses of these. So uses of capacitors. So capacitors are used in things like computers, and they're used in computers as RAM. So basically your memory storage that you have in your computer is actually typically made from capacitors. And basically the way that this works is you'll basically have like a string of capacitors. So let's say you have two capacitors, maybe another capacitor down here. And then what'll happen is this one might be fully charged. So this one might be charged. This one might be charged, so meaning that there's a potential across it so that they have charge on each one, but this one might be uncharged. So meaning that this one has zero charge, but these two have non-zero charge. So what this does is in a computer is that this acts as memory storage. So the capacitors in a computer act as your RAM. So basically when your computer's scanning through, it looks at which capacitors are charged and which ones are uncharged. So this is what creates your binary system. So for example, this is a 1, 1, and 0 when it comes to memory. Right? So when your computer's going through and it's looking at RAM and it's counting which one is 1, 1, and 0. So how these things are aligned and also how they have charge across them will then create your binary code, which will then act as your memory. So capacitors are used all the time, basically in computers. They're also used in surge protectors. So these are also found in surge protectors all the time. So basically, if you had your computer, for example, connected to a power strip which has a surge connector in it, that surge connector is actually just, again, a series of capacitors. And the reason for this is that capacitors block the flow of current. So by the time we get in class and talk about this, we'll talk a little bit more about this. But basically what happens is when I initially connect the battery to the capacitor, charges start to flow through the circuits until this thing reaches maximum charge. So once this has maximum charge of positive Q, this has maximum charge of negative Q, what happens is then no more charges flow through the system, which means that the current, which is the flow of charge, goes to 0. So when this thing reaches maximum charge, there is no more current within inside of my system. So the current is actually equal to 0. So in a surge protector, what this does then is what? Let's say your house is hit by lightning, which then causes a huge amount of potential, which then causes a huge amount of current to want to flow through the system. And what the capacitors do is basically it blocks that flow of current. So meaning that if your computer was connected to your house, through your power plug, instead of having this huge surge of current due to the huge potential source, which would then fry your computer because now you have way too much power going through it, the surge protector, due to the capacitors within inside of your surge strip, would basically block that flow of current, meaning that you wouldn't actually fry your computer or your cell phone or whatever it is that was connected to your house outlet. So these are some basic uses of capacitors. So capacitors are used within inside of, like I said, most electronic devices pretty much all the time. There's also other uses in them. For example, when your car's windshield wipers go off, that's because of capacitors and things, but we'll talk about that when we get there. So again, basics of capacitors. So it's just two pieces of metal separated by some distance, connect that to a battery that then runs current through the system, which then causes this to reach a maximum charge of, say, positive Q, this one to a maximum charge of negative Q, at which point in time the current stops. So again, if I plotted the current versus potential, I find that this is just a straight line. These two are linearly related to each other, where the slope of that line is called the capacitance of the capacitor, and that's only dependent on the geometry. So basically, that brings us to the first part of the lab. So in the first part of the lab, you're going to open up this guy, which is run through Java. So you'll get this through the link. So you just have to download this. So here is our capacitor. So here's just a simple parallel plate capacitor. And then here you can play with a couple things. So the separation distance between the two capacitors, so it goes anywhere from 5 millimeters up to 10 millimeters. And you can also play with the plate area. So basically you're just playing with the geometry, okay? So what I want you to do is turn on all of these things. So we're gonna turn on the plate charge, you can turn on the electric field, the capacitance, plate charge, this is measuring how much charge is across the plates, as well as the stored energy. And then finally turn on the voltmeter as well. So from here, you'll just turn on the battery. So when I turn on the battery, then what you want to do is start looking at these different things. So what you want, so the first part is mostly just making observations. So you're looking at what happens if I increase the separation between the plates? What happens to the charge? What happens to the capacitance? What happens to the energy stored? Do they go up? Do they go down? If I increase the plate area, do they go up? Do they go down? What happens to the potential difference across the plates? Does that change? So here we're going to put it at, again, 1.5 volts. And then from there, switch the battery so that the battery goes in the opposite direction. Redo those observations. So then, once you make those observations, what you want to do then is disconnect the battery. So we're going to put it as, let's see here. So let me undo what I did. Just disconnect it and leave that alone, okay? And then you want to go through all the same stuff again. So basically you want to increase and decrease separation, plate area, and again, makes observations, but you want to try to guess what's going to happen before you actually do that. Is it going to do exactly the same thing that it did when the battery was connected, or is it going to respond differently? So that's the first part of the lab. So the second part then deals with, well, it turns out that when you go to buy a capacitor from the store, you know, like an electronics store, they don't have every type of capacitor ever being, you know, ever thought of being made. And the reason for that is that because companies have to make certain capacitors, and if they made every single type of capacitance that any person might be able to need in all the existence of time, then manufacturing wise, they'd have to basically make an infinite number of capacitors, which would then be costly, and the place would just go bankrupt. Right? They wouldn't be able to actually make enough money to support all the amount of manufacturing that they would have to do. So basically, what that means is we can actually create new capacitors by adding together existing capacitors. So basically, we can create new capacitors by combining existing capacitors. So that means is if you're building a particular circuit and you need a particular capacitance, but you don't have a capacitor which has that capacitance, well, you can add together other existing capacitors to create that capacitance. And the way that you do this is by adding capacitors either in what's called series or in what's called parallel. So let's talk about the difference between each one of these. So let's say, here's my battery. So this is my plus terminal, negative terminal, and that's connected to capacitors. Oops, start drawing resistors. Sorry about that. In a straight line connected together. So let's say here's capacitor C1, here's capacitor C2, here's capacitor C3, and then this guy goes back into the battery. So these three capacitors are connected in what's called series. So they're in series because when I turn on the battery, charges then flow in this direction. So I would have a current running through my system, but that current has to go first through C1 and then through C2 and then through C3. There's no other choice. That's the way it has to go. So this is called series because there is no what's called branching points, meaning the current goes only in one direction and that's it. Okay. As opposed to parallel, where again, here's my battery, say positive terminal, negative terminal. So here, what can happen is I can actually branch off. So I can have C1 here, C2 here, and then C3, say, down here. And then all these are connected back to the battery. Okay. This is called parallel. So parallel is because at these points here, so these ones that I'm drawing right now, these are what are known as junctions or nodes. Which basically means that, again, if I have current running through my system, when I apply the battery, what happens in this case then is the current has three choices. So some of the current is going to split off and go through this capacitor. So this is going to split off and become current, say I1. Some of the current is going to run through the middle section here and go through this capacitor, C2. And then finally, some current is going to split off down here and go through this capacitor. Let's call that I3. But then at this junction here, they have to recombine with each other to then reform that amount of current which is passing through. So this is called parallel. So parallel is the current basically has options. Now, how the current decides which one to go through basically depends on the size of the capacitor. So if you think about, for example, water running through hoses, if I had, say, a big hose running into then, say, three other hoses, right? So these are, say, my three hoses. Okay. So this is the original water flowing in this direction, and then some water is going to go this way, some will go this way, and some will go this way. So the amount of water which goes through each one of these different hoses is going to depend on the cross-sectional size of the hose. The bigger the cross-sectional size, say this one, right, let's call this 3, 2, and 1, more water is going to run through hose 3 because it has the least amount of resistance. It can go through it the easiest. Then the second most amount of water is going to go through 2 because that has a bigger cross-sectional area than 1, and only a little bit is going to go through 1. So basically, the way that the current flows through the capacitors will basically be the same thing. So whichever one has the biggest capacitance will have the most amount of charge, which means it has the most amount of current which goes into it. The one which has the second most amount of capacitance will have the second amount of charge, which means it has the second most amount of current. And then finally, the one which has the smallest amount of capacitance will have the least amount of current which passes through it. So just think about these as basically hoses. So the bigger the cross-sectional area, then the more amount of water will actually pass through them. So good. So basically, the way this works is when I sum these guys together, we can then create a new type of capacitance based off of the way that these things are arranged. Now, it turns out that when these guys are in parallel, and we'll derive this in class, but I'm not going to do it now, is that what we call the equivalent capacitance is actually equal to simply C1 plus C2 plus C3 when these things are connected in parallel, which is then equal to, in a more general sense, the sum over all of the capacitances. So CEQ basically means that what if I combined all this down into a single circuit, so this was plus, this was negative, I'm replacing all of these capacitors by simply one capacitor which has a equivalent capacitance. And that's going to be true for both this scenario and for this scenario. Now, if I connect them in series, it turns out that 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3, or in a more general sense, this is equal to the sum of 1 over all the capacitances. So basically what happens is if I have capacitors which are connected in series, we add the capacitances inversely. So I would add 1 over the capacitance of C1 plus 1 over the capacitance of C2 plus 1 over the capacitance of C3 to then find the equivalent capacitance. So at the end of the day, I have to invert this to find the equivalent capacitance. If they are connected in parallel, we then simply sum all the capacitances together. So here, the equivalent capacitance would just be the sum over all 3 of these different capacitors. So basically, this is what you're doing then in the second part of the lab. So here, you're going to click this button which says multiple capacitors, and then you're going to go ahead and choose different ones of these scenarios. So let me bring up the lab here. So, right, so here you're going to click on total capacitance. So where are we? Let's go to the first one. So the first one is, say, 2 capacitors in series. So here you're going to click on the total capacitance voltmeter in meters, and 2 in series. So if I go back to here, so good. So I would turn on total capacitance, the voltmeter, and I want 2 capacitors in series. Okay. So again, we're going to do the same thing, put this at 1.5 volts. And then what you want to do is measure the amount of capacitance and the amount of voltage across each one of these guys, as well as the amount of charge on each one as well. Okay. And then the second case, you're doing it with 2 in parallel. The third case, you're doing 2 capacitors in series and 1 in parallel. And then the final case, you're going to do 2 in parallel and 1 in series. Okay. So basically, from here, you want to calculate the total capacitance by hand, and then measure that using your the tabs here. And then turn on the battery. You want to measure the potential difference between each of the plates, calculate the theoretical potential difference between each of the plates, and then determine the absolute and relative discrepancies. So between what it is that you calculate and what it is that you measure. So let's see how that's done. Let's do a quick example using this first scenario here. So let's say we have the 2 capacitors in series. So good. Let's see here. So here we want to set the capacitor C1 to 2.2 times 10 to the minus 3. And then C2, I believe we're going to leave the same way. Yeah. Let's do that. So C1, so capacitance, we want to set that guy to 2.2. Is that what it said? Yeah, 2.2 times 10 to the minus 13. Good. So basically what we want to do is calculate the total capacitance. So here we're going to have C2 is 2.2, and then we have C1 is 1. So in this case, we have then the total capacitance. So we have 1 over CEQ, then is going to be equal to 1 over C1 plus 1 over C2. Okay. So from here, we get CEQ then is going to be equal to C1 times C2 divided by C1 plus C2. So this is going to be equal to 2.2 times 1 times 10 to the minus 13 squared divided by 2.2 plus 1 all times 10 to the minus 13. Okay. So here, one of these 10 to the minus 13s will cancel out from this one. So it's going to be the same thing then as what? 2.2 divided by 3.2 all times 10 to the minus 13. And the units of this thing is what's known as a farad. Okay. So this is going to be our equivalent capacitance for this system. Okay. Now, turns out that, let's go back a couple slides here real quick. Turns out that when these guys are connected in series, that the charge across each one of these capacitors is the same. So what this means is that the charge on this plate and the charge on this capacitor and the charge on this capacitor are all identically the same to each other. But since the capacitance is different, that means that the potential difference across each plate then is different. So this is going to have a potential difference of delta V1. This will have a potential difference of delta V2. And this will have a potential difference of delta V3. Now, in parallel, it turns out that this one, and this one all have the same amount of potential difference. So the potential difference across here is the same as potential difference across here, which is the same as potential difference across here. But since all of the capacitances are different, what that means is that the charge on this plate is different than the charge on this capacitor, which is different than the charge on this capacitor. So good. So what that means is what? Now that we know the equivalent capacitance, what we can do now from here is determine the amount of charge which is on both of these capacitors. And the way that we're going to do that is we're going to say, okay, so here I have delta V, which is equal to 1.5 volts, then attached to our equivalent capacitor, so CEQ, which is then attached to our battery. So we can now determine how much charge is across this. Let's call that QEQ. So according to what we wrote down initially, we have QEQ then is equal to the capacitance of CEQ times our potential difference of then delta V. So this is then going to be equal to 2.2 divided by 3.2 times 10 to the minus 13, all times the amount of voltage, which is then 1.5. Okay. So this will then give us our amount of charge. Now that we know the charge on each one of these plates, so let's redraw our original circuits. So that now we know this has delta V. This was our C1. This is our C2. So here we now know that this has an amount of charge of QEQ. This also has an amount of charge of QEQ. So now we can determine the amount of potential. So this says that the amount of potential delta V1 then is going to be equal to the amount of charge, which is QEQ, divided by C1. So this is going to be equal to our numbers. And then simultaneously, we're going to have delta V2 is then equal to QEQ divided by the amount of capacitance, which is then C2. So here you want to theoretically calculate what these are. And then once you do that, you want to come back to here and then measure with your voltmeter what this thing says. So I want to connect my two prongs here and then measure the amount of potential that this says, which is 0.469. And then measure the amount of potential across this one, which then says it has 1.031 volts. Now, compare those then to your theoretical amounts by looking at your discrepancies, both relative and absolute discrepancy. So once you do it then for the two in series, now do it for the two in parallel. And then once you do it for the two in parallel, then do two in series, one in parallel, and then two in parallel, one in series. Okay. It's okay. So again, first part of the lab is just the introduction. So again, this is mostly just making observations. So just write down, record your observations. So this is similar to what we did with the electrostatics lab. And then in the second part, we're playing with these guys. So again, just set all these up. Pardon me. And then, like I said, theoretically calculate the equivalent capacitance, theoretically calculate then the potentials, and then compare those to your experimental results. Okay. So I know that was kind of quick. We'll talk more about these things in class, but anybody have any questions on this at the moment?
So the measured results that we're comparing that to, that's from the voltage meter, yes?
Correct.
Okay.
Yeah. So from the voltage meter, and sometimes you might need the charge, for example. Yeah, so let's see. So this is plate charges. Do that. So this shows the total capacitance. So here you're just going to read off what that total capacitance is. So once you get these guys set, so this will give you the total capacitance. Yeah, and then you should have, so stored charge, is there one for each one? Doesn't look like it. Yeah, so anyways, yeah. So all you're doing is, yeah, you're using these to then measure the potential difference across each one. So you're just reading off what this thing says and going from there. That's right. And in your total capacitance, you'll just get from here. So sometimes you might have to zoom in or zoom out, but anyways, you're just gonna kind of guesstimate what it is off of here. Actually, no, it does say down here. So this says that the total capacitance is 0.67 times 10 to the minus 13 in this particular case. So that's right. So here, when you calculate it by hand versus here, again, you're gonna look at your absolute relative discrepancy, and then again, measure the potential across each one of these individual parallel plate capacitors, and yeah, calculate those out by hand and then compare those to your theoretical values. Okay. So this would be your experimental value. Okay, any other questions on that? Or doing okay? All right. Well, I'll be here. So if you have any questions that you run into as you're playing with all that stuff, feel free to ask. Yeah, I'll be here for a while. Okay.